Okay, so on this example, it says today the waves are crashing under the beach every 4.8 seconds. The times from when a person arrives at the shoreline until a crashing wave is observed follows a uniform distribution from 0 to 4.8 seconds. Round to four decimal places where possible. Okay. So the key word here is uniform distribution. So what that means is, every 4.8 seconds, a new wave comes in. So if here's the shoreline, and the wave comes in, 4.8 seconds later, a new wave comes in, new wave comes in every 4.8 seconds. So if you just show up at the beach, at the shoreline all of a sudden, um, you could see the next wave come anywhere from 0 to 4.8 seconds, depending on when you show up in that interval, right? You could show up halfway right in the middle, between two waves, and 2.4 seconds later, you'll see the next wave. Or you could show up right after the last one and wait almost 4.8 seconds. Or you could show up right before another one comes and just wait like a part of a second, and it just comes right away. So, um, the times from when a person arrives at the shoreline until a crashing wave observed follows the distribution from 0 to 4.8 seconds. So that's what we're talking about. If you show up at the shoreline, or a person shows up, arrives at the shoreline, how long is it going to be till they see the next wave? Well, anywhere from 0 to 4.8 seconds because they come every 4.8 seconds. Okay. What's the mean? Mean means average. So what's the average time it'll take if a person shows up at the shoreline, right? Arrives at the shoreline. What's the average time it's going to take for them to see the next wave? Well, the average time is 2.4 seconds. Why? Because that's the average of the A and the B. The A plus B divided by 2. That's the formula. Let me show you the formula. Here's the formula. This is the chapter 567 notes. The mean right there, A plus B divided by 2. A and B are the uniform distribution from A to B. So add those two up and divide by 2. So in other words, this is the A and this is the B. So it's going to be 0 plus 4.8 divided by 2. It's going to be 4.8 divided by 2. Your calculator will tell you it's 2.4. Now, so that is the answer. And it makes sense, doesn't it? Because that's got to be the average. You know how to find the middle of two numbers, the average of two numbers. You add them and divide by 2. So the middle of 0 and 4.8 is 2.4. It's halfway. So that means on average, if you just show up at the shoreline randomly, on average, the average wait time for the next wave is going to be 2.4 seconds because on average, you'll arrive right in the middle. I mean, you think, well, how do you know? You might arrive early or late. Yeah, you might. The average will be, sometimes early, sometimes late, but overall, the average is right in the middle. You'll arrive right in the middle and it'll be 2.4 seconds. Sometimes it'll be longer, sometimes it'll be shorter, but the average will be 2.4 seconds. All right, next question, standard deviation. How much deviation is there going to be from that average? Well, just grab the formula. Standard deviation is right there. Width, b minus a over square root of 12. So we just go, oh, okay. So it's b minus a over square root of 12. Again, b and a, so 4.8 minus 0 over the square root of 12. So that's 4.8 over the square root of 12. Okay, let's go to the calculator we're going to use. If you click on the calculator on the home page, you get this thing, right? You can go to any one of these other than number one. Let's go like to number two, anything but number one. It'll pop up. We're not going to use the main calculator on the page. We're just going to go to the bottom now. The very bottom, see it says scientific? Click on that one. There we go. We can do this. So click the fraction maker button, 4.8 on the bottom, go square root of 12. There we go, 1.3856. So we go back, 1.3856. There's the answer. And what does that mean? That's the average distance from the middle. Notice the average person who shows up at the shoreline will wait 2.4 seconds, half the time for the next wave. But not everybody's going to wait exactly 2.4. Some wait longer, shorter. How far are they going to be off of that? They're going to be off of that by 1.38 seconds typically, more or less, longer or shorter wait time, right? The average person will wait 2.4 seconds, but not everybody's right on the average. Some are higher, some are lower. How far are they off of that? Typically, the average distance from the middle, that's standard deviation, is 1.38 seconds. So they might take, 2.538, or shorter by 1.38. All right, we got it. Let's move on. Probability that a wave will crash under the beach exactly 3.6, and that's 0. They might wonder, no, that could happen. It could happen exactly. No, it can't. Think in the math and science, we're being real here. Something's never going to happen exactly 3.6. You might say, yeah, no, I clocked it. You just, whatever instrument you have in real life, though, it probably was 3.6000001. It's a little bit longer, or maybe just a little bit short, 3.599999987, or something. It's not gonna ever be exactly. I mean, exactly. In math and science, when we say exactly, we mean exactly. There's no way in the world it's going to be exactly anything. 3.6 or any other number. It's never exactly, because it's always going to be off a little bit. So whenever they say exactly, the answer is 0. The chance of that is 0. That's in the notes. Whenever they say exactly one value, it's 0. It's impossible. Never exactly 3.6 seconds. You're always just a little bit more or a little bit less. No way to be exact, right? If you're exact, you might think, well, it's just all about the precision of the tool you're using. But I think, yeah, I clocked it was that. Well, if you had a more precise chronometer, way out there, it's probably a 1 or something. It's just you'd have to have zeros forever, forever to be exact, and there's no way. It's impossible. All right, no such thing as exact for a uniform continuous distribution. All right, well then what's the chance it'll be between 1.7 and 4.1? That could be, that could be. So how would that happen? Well, probability. Probability is always the number we want over the total things that are possible. What do we want? We want to be between 1.7, 4.1. Well, how wide is that time interval? Just subtract those. You'll find out how many seconds in that interval, whatever Desmos tells or the scientific calculator tells us. On the bottom of those, the total. What's the total? 4.8 minus 0. I'm getting this out of the formula here on again, the notes. Probability between, it's the width of the section described over the overall width b minus a. So the section described is between 1.7 and 4.1. So subtract those, get how many seconds in that interval. You can hit the button, so you calculate it's going to be, I think it's 2.4 over 4.8. Notice that's a range of 2.4 seconds. Want the next wave to come somewhere between 1.7 seconds after we arrive and 4.1 seconds over, it could take anywhere from 0 to 4.8 over a 4.8 section interval total. What's the chance it'll be in that range? If you divide them on your calculator, it'll be 0.5. There's a half chance. Because why? Because that's half the range. 1.7 to 4.1 is 2.4 seconds. It's half of the total range that is possible. So there's a half chance it'll come in that range. All right, next, it says the probability will take longer. Well, same kind of thing. It's the number we want over the total. So we always do probability, right? What's the with longer than that? That's going to be 4.8 minus 3.76 over 4.8 minus 0. Why is that? Well, because how much time is in the interval longer than 3.76? It's, from 3.76 all the way up to 4.8, because that's the most, right? A new wave comes every 4.8 seconds. Over the total width, it could happen anytime between 0 and 4.8 seconds. So go to Desmos, minus 3.7, or the scientific calculator, 4.8 minus 3.76. I'll do parentheses divided by 4.8. There we go. 2.1, 0.21, 6 is the rest of the way. So, point, 0.21 with sixes. You could just put in a whole bunch of sixes like that, or you could round the last one to 7. It'll take it either way. So, all right, next. Now, here's where things get a little more tricky. Suppose that the person has already been standing at the shoreline for 1.3 seconds without a wave crashing in. That's a condition. They're giving us now a condition, right? They've 1.3 seconds without a wave crashing in. Find the probability that it will take between that and that. Well, come up here. It's going to be this form. It's given or conditional probability. Width of the section described over total section width possible given that condition. So it's going to be width of the section described over um, total width given the condition. Okay, let's see if we can make some sense out of that. So there's the condition, as it says up here, condition. You've been there 1.3 seconds without a wave crashing in. So that means it could come anywhere between 1.3 and 4.8, right? That's the total width given that you've already been there 1.3 seconds. Obviously, the wave didn't come between 0 and 1.3 seconds. So it's going to come somewhere between 1.3 seconds and 4.8 seconds. It's going to come somewhere in that time interval, given the condition that we've already been there 1.3 seconds without a wave coming. And then the top is, what's being described. You want it between 1.9 and 4.3. So there we go. Let's go to the scientific calculator. 4.3, 1.9, 4.3, 1.9 over 8 minus, was it 1.3, I think? 0.6857. 0.6857. There it is. Yeah, so that makes sense now. Um, so again, for condition, when they give you a condition like, hey, you've already been there 1.3 seconds, no wave. So that means the bottom, the top's the same as the other tops, right? Just like this top, that top, whatever. They say we want it between 1.9 and 4.3. Just subtract those. Just like the last one, right? Or two go between 1.7 and 4.1. Same thing. The bottom's what's new. When you're given a condition. So the bottom is no longer 4.8 minus 0 like it was in the last two. Why? Well, because we know it didn't, we've already been there 1.3 and the wave hasn't come. That's the conditional given information. It didn't come in the first 1.3. So we know it's going to come somewhere between 4.8 and 1.3. That's what we're given different. Whereas back on this one and this one, it could have come anywhere between 0 and 4.8. So the bottom was 0 and 4.8. We didn't have any prior information. We've already been there a minute or 10 seconds or, well, it's too long. We've already been there 1 second. This time they say we've already been there 1.3 seconds. No wave yet. So we know it's coming somewhere between 1.3 and 4.8. That's the longest because it comes every 4.8 seconds. And then so that's the denominator, and the top is like what we always do. There's the answer. Now, let me mention, sometimes they'll say the same question differently. They'll say, right out here, they'll say, um, oops, there we go. They'll say, what's the probability X, or they'll say X is between 1.9 and 4.3. That's between, right? That means between. And then they'll go straight line, which that stands for given, between these, given the condition that we know X is greater than 1.3, right? Because you've already been there 1.3 seconds. So they're saying, what's the chance that the X, the time that you're going to wait, is going to be somewhere between 1.9 and 4.3? So that X is between 1.9 and 4.3, between 1.9 and 4.3. Given, straight line means given that you already know X has got to be greater greater than 1.3. How do you know? Well, because you've already been there 1.3 seconds and the wave hasn't come yet. So you know the time for the wave to come is going to be greater than 1.5. So you're given, the condition that X has got to be something greater than 1.3. So what's the chances it's going to end up being between 1.9 and 4.3? So sometimes they'll write it this way, and sometimes they'll give it words. But when you see that straight line, you know it's given. You go grab the given formula. And the top is like we always do, just subtract those. The bottom, though, changes because the given condition changes the fact it's not 4.8 minus 0. We know it's greater than 1.3, so it's 4.8 minus 1.3. All right, enough said on that one. Let's move on. So we've got a couple more here. Let me bring it here. So part G. G says 20% of the time a person will wait at least how long before a wave crashes in? Yeah, that's a tricky question. Let me help with that one. If you think about, it's a little short. If you think about, the waves coming from 0 to 4.8 seconds, right? We know that from the beginning, right? And, between 0 and 4.8 seconds, there's all, when you arrive, because a wave does come in every 4.8 seconds. So when someone arrives all of a sudden at the shoreline, they're going to see the next wave come in somewhere between 0 and 4.8 seconds, depending on when they arrive between waves, right? So, okay, so every person that shows up at the shoreline, it'll be between 0 and 4.8 seconds before they see the next wave, depending on when they arrived between waves. Okay, great. So what? And then they're saying, well, 20% of the time a person will wait at least how long? Well, Remember, at least means more than. So my point is, they're saying the top 20%. They want to know what time will put you in the top 20%, right? 20% of the time, a person will wait at least how long? At least means this, this or more. The least. They want the least, but it could be more. It could be all the way up to 4.8 seconds. That's what they're saying. So you think, oh, that's tricky. Right. So that means that this is 80%. You see, if this is 20, this is 80%. So we're looking for the time. What time is it? Like 4 seconds, 3.8 seconds, 4.1 seconds. What is the time that puts you in the top 20%, meaning 80% of the people waited less time than you to see the next wave? That makes sense? You show up at the shoreline. We want to know the time. 20% of the time, a person will wait at least how long? So 20, what is the time such that 20% of the time you're going to wait that time or longer, the least you're going to wait. Whenever we say least, it's that or more. That at least means that or more. So it means to the right. That's why I did 20% on the right, 80% on the left. You might wonder, why didn't you put 20% down here? Well, because that's what at least means. It means on the right. If I say the least number of kids I have is three, that means I have three or more. The least number of pins in my pocket is five, means five or more. The least I could have is five. I might have more. So we want to have what's the least time such that 20% wait that time or more. What is it? So that means it's 80% along the way. So we're going to say, oh, so it's 80% it's 80% of our 4.8 second time interval. Is that making sense? It's 80% of that. So that's 0.80 of means times 4.8 seconds. Go to the calculator. 0.80 times 4.8. 0.80, 80 times 4.8. 3.84. 3.84. So this time here is 3.84. That's what we got. Meaning 3.84 seconds, 20% of the people wait 3.84 seconds or longer, wait at least 3.84 seconds for the next wave to come, because that's 80% of the way between 0 and 4.8. 80% of the way times 0 to 4.8. So that's the answer to that. Um, the formula I used there was this one, but it's more complex as I would just encourage you just to think the way I did. Top 20%, that means you're 80% along the way between 0 and 4.8. So you're 80% of the 4.8 seconds, right? So 80% of the 4.8 seconds is 3.84. So 80% of the people wait 3.84 or less, 20% of the people wait 3.84 or more, at least 3.84 seconds. Final question, find the maximum for the lower quartile. So that is again, quartile is a percentile number. Remember, 0 and 100%. Quartile is like a football game, basketball game, 50% halfway. 25% there, 75% there. So first quartile is, there's the lower quartile, right? And here, right here is the max of the lower quartile, right? The maximum for the lower quartile. So it's right there. That means for the lowest quarter, what's the maximum value in that lowest quarter? How do we find that? Well, that's the P equals 25. It's 25% of the way through the data set. So go grab the P formula. It says right here, by the way, end of a quartile, first quartile, P is 25, second 50, third 75. So we just use this formula. Again, we're going to say 25% of the way through the data. So I go, okay, so P equals A plus, what is the formula? Plus P over 100 times the width. P over 100 times B minus A. So that means the P formula is going to be A. What's A and B? Well, A is right here. A is 0, B is 4.8. A is 0, B is 4.8. And P is 25. So if you hit the buttons on the calculator, that 0 is not doing anything. 25 times 4.8. That makes sense, right? It's just like the last one, really. It's similar. I mean, because from 0 to 4.8 seconds, that's the whole range, 4.8 seconds. We want to go 25% through that interval. So if you multiply 25%, 1/4 of that interval, what's that going to be? For 1.2? Yeah, 1.2. 1.2. So 1.2 seconds is 25% of the whole interval, is the end of the first quarter for that whole interval. And so there we go.